directly proportional to the product of their masses and inversely proportional to the square of the distance between. So the SI unit will be FR square divided by mm. So FR square, that is nothing but Newton meter square divided by mm. So again, if you ever want to calculate acceleration due to gravity, that is G is equal to gm divided by r square. If this is the earth, initially if we go in, it is true that the radius actually decreases. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we are going to start a new chapter, that is gravitation. So we all have heard about gravitation, what is gravity, what is universal law of gravitation, all this from the high school level, but now we are going to take a look at it a bit more deeper and see what are the specialities of gravitation. So before diving into gravitation, let's look at the man who actually discovered gravity. Not invented, but actually discovered. So the story goes on that he was sitting under an apple tree, the apple fell on his head, and incidentally he discovered gravity. So that is not the actual case actually. So what happened was that Sir Isaac Newton was actually a student in Princeton, his esteemed university, and what happened was during the plague time, he was given a holiday, just like we got holidays for coronavirus, like everyone got holidays for like 2 months, 3 months and all that. He also got holidays and he was back in his home, and while he was in his home, he researched a lot, mainly on optics and several other mathematical phenomena. But let's focus on gravity. So what happened was that one fine day he was walking through his estate and he was resting there. And he happened to saw that an apple fell to the ground. So he was walking through his estate and he saw one apple fell. Or he was resting somewhere and he saw one apple fell. So he was like, why didn't this apple fall to the side or towards the left? Or why didn't it go up? Why just down? Always things just fall down. Is it because of what Aristotle said, like the earth yearns for every object to fall onto earth? No, right? We absolutely know that that is not true. So the famous question came, if an apple can fall, can the moon also fall? Or is the moon falling? That was the question Isaac Newton actually had in his head. If an apple can fall, can the moon also fall? Because for everyone till that date, moon, sun, stars, everything was fixed in the sky, right? Even though it's moving, nobody imagined for the moon to fall onto the earth. Nobody imagined the sun to fall onto the earth. We jokingly say that the sky will fall onto our heads for those who lie. So like that, we say we never imagine a situation where the moon actually falls onto the earth. So Isaac Newton actually asked this question, and that is when he actually discovered a mathematical relation between what he felt. Again, you have to understand that Newton saw the world in terms of lines of forces. So that is how he actually explained all of this. And he did not actually give a definition for gravity. He only described objectively, that is what gravity is, what are the properties of gravity, how it interacts. And all these phenomena were actually explained by Newton. It is not a definitive statement saying, okay, this is what causes gravity. This is the reason for gravity. He did not do that. That was Einstein who came up with the theory of relativity, and he explained what gravity actually was, which is bending the space-time curvature. And now we are researching more on that regarding gravity, that is what is graviton and all that. But okay, that is all higher order physics. For you, the only thing you have to understand is that as Isaac Newton went on with this incredible discovery and he dove into mathematics and found out several relations, one particular relation he found out was that, okay, gravity is a force of attraction. Even though it's very weak, actually it is the weakest force, that is, it is even weaker than any other forces in the universe. It is so weak, but it is also actually a long range force. All that, let's keep all that aside. The important thing is that he figured out, okay, if there are two masses present, let's say at any particular distance, if there are two masses present, they feel an attractive force between them. So these two masses yearn to be together, to quote Aristotle. So two masses will have a positive sense of attraction towards each other. That particular force is felt in between them is known as gravitational force. So Newton's laws of gravity, it's actually known as universal law of gravity or universal law of gravitation is what the particular law is called. And what it states is that if there are two masses, let's say mass m1 and m2, if there are two masses, let's say separated by a distance of r, then what Newton said was, what Newton found out mathematically was that these two masses will experience a force of attraction between each other. So these two masses will feel a force of attraction between each other, which is directly proportional to the product of their masses and inversely proportional to their relative distance between them, square of the distance between them. That is, Newton found out that, okay, the force experienced that. In this particular case, it is gravitational force. So Fg. So this particular force will be directly proportional to the product of their masses, and this particular force will be proportional to the inverse of square of the distance between them. That is, this is how gravitational force affects distance and how it affects masses. So he put together this equation and he concluded that, okay, so I can say that gravitational force between two masses will be such so that the force will be directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Now, in order to avoid this proportionality symbol, later a proportionality constant was introduced, and that was introduced, and you can calculate that particular constant using the Cavendish experiment. So I'm not going to discuss what the Cavendish experiment is. If there are any curious minds, you can go Google it out and find out what the Cavendish experiment is. At the end of that particular experiment, you can actually calculate the exact value of what was the gravitational constant, or in this particular case, the universal gravitational constant, capital G. You can actually find that using the Cavendish experiment. You can feel free to do that particular experiment. But now, a constant of proportionality was actually introduced to this particular equation. Then we know that the famous equation came into effect, that is F is equal to capital G, which is known as the universal gravitational constant. So capital G m1 m2 divided by r square. So this is the famous law that is stated as Newton's law of gravitation, but the actual name of the law is universal law of gravity or universal law of gravitation. It is universal, which means not just here in Earth, in Mars, in Moon, at the edge of the universe, wherever you go, this particular law holds, which means that it is true everywhere in the universe. That is why it is a universal law. So everywhere in the universe, if there are two masses, they will experience a force of attraction towards each other. And as we move away from those masses, as the two masses increase in distance or the separation increases, we can say that the force decreases by 1 by r square. So you know what inverse squares are. So the strength actually decreases. If two masses, let's say 1 kilogram on 1 kilogram, are kept 1 meter apart, the force will be high. If it is kept 2 kilograms apart, then what happens? Automatically it becomes 1 by 4. Initially it was 1, then it became 1 by 4. Then if it is 3, it will become 1 by 9. Like that, it will increase. That is, the force will actually decrease. As the radius increases, the force will actually decrease. So that is one thing you have to bear in mind. And the definition is the explanation of this particular equation, that the force experienced between two masses is actually directly proportional to the product of their masses and inversely proportional to the square of the distance between them. That is known as universal law of gravitation. And the SI unit of universal law of gravitation is, what is the SI unit of universal law of gravitation? That is F is equal to G M M by R square. What will be the units? Are you going to calculate everything? Alright, it's force on the left hand side. Obviously, it is going to be Newton. So the unit SI unit is Newton. But they can ask you what is the SI unit of G? Gravitational constant. What is the dimensional formula of G? Then you can just rearrange the equation and you can just calculate it. It's that easy. So again, F is equal to capital G M by R square. So again, you can use M1 and M2 or just one capital M and one small m. This is mainly used when we are talking about Earth attracting other objects. That is when we use capital M, considering this M as the mass of the planet. Again, so we know what is the mass of the planet. We can measure what is the distance between two particles. We can measure the mass of the second body. But what is G? So G is the gravitational constant and it has a value of 6.67 into 10 raised to minus 11. That is the value of the gravitational constant. So the SI unit will be FR square divided by mm. So FR square, that is nothing but Newton meter square divided by mm. Mm is nothing but mass into mass, that is kg into kg, kg square. So you can write it as Newton meter square per kg square or Newton meter square kg square inverse. That will be the SI unit. Dimensional formula you can calculate on your own. So that is all about universal law of gravitation. Again, I am not stressing on it too much because you have already heard about it a million times from your high school. Now, the next culprit, nothing but acceleration due to gravity. So what exactly is this acceleration due to gravity? Obviously, it is an acceleration because it is written here, it is acceleration. So acceleration just means that rate of change of velocity. So we know that in order to produce acceleration, there should be some force. Without any force, there cannot be any acceleration. Now, we know that that particular force responsible is nothing but gravity because it is acceleration due to gravity. So the force who is responsible for producing that particular acceleration is nothing but force due to gravity or simply gravitational force. So gravitational force is the force which is pulling down on any object, changing its velocity. That is, if this is Earth, let's say this is Earth, if I let go of any object here, it will come down to Earth with a particular velocity. Now, at each second in time, since the radius is decreasing between the center of the Earth and this particular object, the gravitational force will actually increase, which means that with increasing force, the Earth will be pulling down on this particular object, which means that this object is going to be accelerated towards the center of the Earth. Obviously, it won't go to the center of the Earth, it will stop somewhere on the surface, but again, its effect will be felt as if something is pulling it towards the center. So this particular pull is known as the force due to gravity. And since the acceleration is produced due to that gravitational force, we call it as acceleration due to gravity. And its value is actually given by, 9.8 meter per second square. How we get this value, we'll just find out very soon. But again, this much you have already heard in your high school and even in your upper primary schools also. 6, 7, 8, 9, 10, you have seen all this. Some of you round it up to 10 meter per second square also. Again, why it is 10, will it be 10, will it be 9.8 everywhere? All these things we'll see very soon. But for now, know that this particular acceleration that is produced due to gravity is known as acceleration due to gravity, which is indicated by the small letter g and is given by 9.8 meter per second square. Now again, it just means that what it actually means is that at every second, if I measure this velocity change, at every second, the Earth is going to pull down on this object, and at every second, the speed is going to change. That is, it is going to increase by 9.8 meter per second square. At every second, if it is starting from, let's say, 1 meter per second, then the very next second 9.8 will be added, which means it is accelerating at every second. But we obviously know that if that is true, then any object that is dropped at a particular height will hit the earth at incredible speeds, right? But that is not the actual case. That is because there is something known as wind resistance. So this wind resistance will actually oppose this particular incoming motion. That is, it will oppose and give friction. The frictional force will be acting against the incoming object, and after some time they balance it out, and the object will attain what is known as terminal velocity. It is because of this frictional force that you see rockets and everything, when entering into Earth's atmosphere, they would start to burn up. You can see a red glow and everything. That is because the air molecules, the gas molecules are hitting and colliding with the object, making friction and causing friction to burn the object. That is, increase the heat on the object. That is why all this happens. But again, when the object is falling, because of air resistance, the velocity is actually cut down to what is known as terminal velocity, where above which the velocity won't actually increase. So there is something known as terminal velocity. You don't have to worry about it, because since you're considering all ideal cases, wind resistance is actually neglected for all of you. So for you, there is no wind resistance. So you can say that acceleration due to gravity will pull down on an object, and at every second the acceleration will increase. That is all the things you have to know about acceleration due to gravity, and ignore wind resistance. Now you know the definition for acceleration due to gravity, but how did we actually find out what is this particular force, or what is this particular acceleration due to gravity? Again, we use Newton's simple equations in order to find what is acceleration due to gravity. We know that by second law, F is equal to ma. Here, what is m? M is the mass of the object that is pulling us towards it. For example, if I assume a case where Earth is pulling down on something, then I can say that m is the mass of the Earth. So I can simply say that F is equal to capital M into A. Or simply, to find out this particular acceleration, that is, what is the acceleration produced by Earth, we can simply rearrange this equation. That is, so F by M will be equal to A, which is nothing but acceleration being produced. So if I know the mass of the planet and what force it is applying, then I can calculate the acceleration due to gravity. So since this particular acceleration is produced by Earth due to gravity, that is force of gravity, we can say that, okay, F by M will be equal to G, which is indicated as acceleration due to gravity. So if force is given, mass of the planet is known, then you can actually calculate the acceleration due to gravity. So what if you don't actually know what force is being applied? Then there will be a problem, right? If you don't know what is the force being applied, then it will be a problem to calculate the acceleration due to gravity. Never fear, we have another method to calculate acceleration due to gravity, because you're going to find out what is the value of acceleration due to gravity all on your own. Again, I told you one method is F by capital M will give you G, but for that you need to know what is the force being applied. What if you don't know the force being applied? Then you can use one more equation, because we already know that F is equal to ma, which we use to find out this relation. But then again, if I don't know the force, that is a major problem. So then what do? We use the second equation, that is simply F is equal to G m divided by r square. Here the capital M is indicating the mass of the planet, the mass of the smaller object. That is, if I am considering Earth and if I am considering something small that is falling towards Earth, then this particular M is the mass of the smaller object, and the capital M is the mass of the planet which is pulling on it. So again, since both are forces, I can actually equate these equations, which means I can write F1 is equal to F2. That is, F1 is equal to F2. Or simply, MA is equal to GMM divided by R square. Now, the trusty cancelling out comes in, because M and M cancels out. So we can actually say that A is equal to GM divided by R square. Or simply, G is equal to gm divided by r square. Now why is it g? Because here the acceleration is produced due to gravity, so we call it as acceleration due to gravity, hence we call it as g. Now this particular derivation, if you do this calculation, that is gravitational constant times mass of the planet divided by the radius of the planet, you will actually get the acceleration due to gravity at the surface of Earth. You can actually do that. You can actually find out what is the acceleration, and it will be approximately equal to 9.7 something meter per second square. We round it off to 9.81 because that is the maximum acceleration we feel at the surface of the Earth. Anyways, this also gives us one important principle, that is the acceleration due to gravity does not depend upon the mass of the object falling. It only depends upon the mass of the planet or mass of the object which is attracting that particular smaller object. If I keep one heavy bowling ball here and it is falling down to Earth, right next to that, if I keep, let's say, a feather, if I keep a feather like this, then both the bowling ball and the feather will fall together. The bowling ball and the feather, let's say I am keeping it at the same height. Let's say entire air resistance is neglected. It is completely vacuum. Then what happens is that both the feather and the bowling ball is let go at the same time. What will you imagine? You will imagine that, okay, the bowling ball will fall first and the feather will slowly fall down, right? No. In the absence of air resistance, we can say that since acceleration due to gravity is independent of mass of the object falling, we can drop one elephant and one ant at the same time. One elephant and one ant. It will be falling at the same rate because every object is accelerated at 9.8 meter per second square. One object is not going to exceed the other object. So in most movies, like where the heroine is cut or stabbed and she falls off from some place, the hero after 5 or 6 or 7 seconds, he will jump down and magically they will both fall at the same rate, which is not actually possible. It is not according to the rule of physics at all possible because acceleration due to gravity is independent of mass of the object falling. That is why during free fall, we don't experience any weight also because we don't have any reaction force upwards. We don't feel any weight also, and we'll be falling under the influence of the planet's mass and not our mass. So this is all just a few things you have to remember because you're studying physics. So again, if you ever want to calculate acceleration due to gravity, that is g is equal to gm divided by r square. You can do that because the value of g is already known, which is 6.67 into 10 raised to minus 11, and mass of the planet is around 6 into 10 raised to 24 kilograms. Radius of the planet is nothing but approximately 6400 kilometers, or it can be written down as 6400 into 10 raised to 3 meters. So you can actually substitute these values and you'll get acceleration due to gravity approximately 9.79 something, but if you're in the polar region, if you take actual correct values, you'll get it somewhere around 9.8, 9.81. So that is why we approximately take 9.81 meter per second square as the default value for any calculations. So that is the value of acceleration due to gravity. So I think we have established that, okay, acceleration due to gravity is 9.8 meter per second square. There is a force between two masses. It will pull down on the masses and blah, blah, blah. All true. Now, my question is, what if you're standing on a building? Let's say you're standing on the tallest building that man has ever built. Let's say you're standing on the Empire State Building or Burj Khalifa, or you're standing on the Statue of Liberty or something. You're standing at a huge height. So my question is, will the acceleration due to gravity be same at this particular height? Let's say this is about h. So if you're standing here, will the acceleration due to gravity be same or will it be different? Of course, sir, it will be different. Since we are way up in the air, the acceleration due to gravity will be lower. On the surface, we will feel that to be 9.8 meter per second square, because again the equation states that G is equal to capital Gm, which is gravitational constant, mass of the planet, divided by r square. R square is nothing but radius of the planet. Now I am standing a little bit above. There was a smart student. So, but sir, this particular height is very small compared to this radius. So there won't be any much increase. That is also true. At very small heights, there won't be like such huge difference. But we also need one general expression. That is, as height increases, does gravitational force, that is acceleration due to gravity, does it increase or decrease? If it is decreasing, but what rate is it decreasing? Okay, one more question is that if I want to feel more gravity, if I dig down onto earth, let's say I am digging down onto earth and I'm coming in like this. If I'm coming in and I'm at a particular depth, let's say at D depth, will I feel more gravity or less gravity? Sir, yes sir, the radius is decreasing, so obviously we'll feel more gravity. Is that the truth? So this is two instances we have to prove right or wrong. These two doubts has to be cleared very quickly. So the first case we are going to consider is that acceleration due to gravity at a certain height, h. Acceleration due to gravity at a certain height, that is h. What will happen to the gravity? Let's see. So now, since I'm going to find out what is GH, what is the relation between GH and G, or simply what is going to be the effect of gravitation, that is acceleration due to gravity at that particular height, I'm going to divide these two equations, that is, I'm going to divide equation 2 divided by equation 1. So that implies that equation 2 is nothing but GH divided by G, or simply Gm divided by r plus h whole square divided by Gm divided by r square. So immediately Gm and Gm cancels out and it will be r square by r plus h whole square, right? So if you don't know how to do this, just apply reciprocal multiplication, that is, it will be Gm divided by r plus h whole square, that is 1, multiplied by r square divided by Gm, right? So here the Gm and Gm will cancel each other out and it will be r square divided by r plus h whole square. So this will imply that this will be equal to r square divided by r plus h whole square. Now, since I'm trying to find out what is GH, or what is the relation between G and GH, I'm going to rearrange this particular equation. So for that, I'm going to take r square outside of this particular equation. This is r square, r plus h whole square, right? So I'm going to take r square out of this particular equation, which means this can be written down as r square by r square into 1 plus h by r whole square, right? If I take r outside from here, I have to take r from here also. There is no r here, so I have to divide it by an r. So you'll get 1 plus h by r. So this r square and r square cancels out, and what I get is that gh divided by g is actually equal to 1 by 1 plus h by r whole squared, or simply this g, if I drop it here, I have an equation for acceleration due to gravity at a particular height, which means I can write this as gh is equal to g by 1 plus h by r whole square. So I have an expression for What is acceleration due to gravity at a particular height from Earth's surface? So this is generally applicable anywhere. As the height increases, what happens? As the height increases, the entire denominator value increases. So it's common sense, right? As height increases, the entire denominator value increases, right? So if the entire denominator value increases, obviously GH will go down. As the denominator of any quantity increases, the entire net quantity will decrease. 1 by 4 will be less than 1 by 2. 1 by 8 will be even less. 1 by 10 will be even less. 1 by 100 will be even less than that. So as height increases, the acceleration due to gravity also decreases, because with height this goes down. So that is why with height we can definitely say that acceleration due to gravity actually goes down. Now, let me get back to that smart guy's question. That is, what if the height is very less? That is, it is very close to the surface compared to r, that is compared to the radius of Earth. What if the height is very less? Then what happens? Do we have to take this particular equation? Because it will be very less, right? If I climb even Burj Khalifa, or if I climb the pyramids also, if I climb the Statue of Liberty or Empire State Building, whatever it is, it won't be even comparable to this particular radius of Earth. So when this particular h is very low compared to the radius of Earth, then do we have to use this particular equation? Actually, we do. There is actually a variation in acceleration due to gravity with height. Now, this is actually for a lot of heights. That is, if you're going or launching a really high space tower or something, space antenna or something, you're taking and climbing up some stairs or something, then actually this equation value matters. But what if the height is significantly less, very close to Earth's surface? Then you can actually modify this particular equation. This equation actually stands, but it should be slightly modified. So, in cases where h is very less than r, right? In cases where h is very less than r, which means at small heights from the surface of the Earth, let's say at 10 kilometers from Earth's surface, or like 1 kilometer from Earth's surface. Like even the tallest building is just 1 kilometer or 1.5 kilometers high. So it is not like 10 kilometers height is there. So in that particular cases, what will be the acceleration due to gravity? For that, we have to actually apply what is known as binomial theorem. So there is actually a binomial theorem which you have already learned in your mathematics class. So there is a binomial expression that states that is, using binomial theorem, there is an expression where 1 plus x whole raised to n, that is this particular case, 1 plus x whole raised to n can be approximately written as 1 plus nx. So there is a binomial theorem result that states that 1 plus x raised to n in certain cases can be written down as 1 plus nx. So when this h is very less than r, that is, when this h is very less than r, we can apply this binomial theorem result and we can actually say that, okay, using binomial theorem like this, I can actually say that 1 plus h by r whole raised to 2 will actually become, so this is actually 1 by 1 plus h by r whole square. So this actually can be written as this 1 by, in order to avoid that, how can we write that? Yeah, we can write it as the inverse. So we can actually write it as 1 plus h by r whole raised to minus 2. So 1 by x square can be written as x raised to minus 2. Same logic. So if I apply this binomial theorem here, then this will become 1 plus minus 2h divided by r. Right? 1 plus minus 2h divided by r, or simply 1 minus 2h divided by r. So applying this, you can have one equation that states that, okay, at very low heights, you can say that acceleration due to gravity there will be again represented as 1 minus 2h divided by r. So again, there is not much difference in the physical significance. That is, as height increases, g will go down. That is true, but comparatively, it won't be a drastic difference like when we are going out of space and comparing that particular gravity to Earth. So that is actually different, but this is more of a practical case which we can actually experience on Earth. Now again, the second case, which is again much more simpler, what happens to acceleration due to gravity at a depth, let's say, of d. So if this is the radius of the planet, I'm standing at a depth of d. What happens to acceleration due to gravity then? Right. So what happens to acceleration due to gravity at depth d? Instead of going up, we are going inside the Earth. So what happens to the acceleration due to gravity? Sir, it increases because r is becoming less, sir. So the acceleration due to gravity has to increase. Let's see if the acceleration due to gravity increases or decreases. So again, I'm going to consider this entire Earth of mass m in terms of its density, because again, you know what density is, right? You have already learned in your high school what density is. Density is nothing but density, which is usually represented by rho. Again, this is rho. It is the Greek symbol. So again, it is represented by rho. So rho is equal to, or density is equal to, mass divided by volume, right? Mass by volume is density. Or simply, in order to represent mass, I can simply say that rho v will be equal to mass, right? Again, if density is equal to mass by volume, then automatically mass is equal to density into volume. That is very simple, right? So I'm going to write this particular equation or express this particular equation in terms of its densities. So then we can actually get a clearer comparison. So again, before all of that, we'll start from the beginning. That is, g at the surface, g will be equal to gm divided by r square, which is common. Now let's name it as equation number 1. And next, we are going to take g at a depth, which is gd, is nothing but gm divided by r. It was plus d, now it is, sorry, it was plus h, now it is going to be minus d because we are going inside. So it is r minus d whole square, right? Once it was r square, now we are going inside, which means that much distance has to be subtracted from that particular radius. So r minus d whole square. Let's name it as equation number 2. That much is clear. Now again, the density part comes in. Now I'm going to express these two masses in terms of densities. So we can say that, okay, gs will become g into, instead of m, we are going to write rho times v. That is, instead of m, we are going to write rho times v divided by r square. Again, for gd also, we are going to write g rho times v. Let's take this as volume number 2 and divided by r minus d whole square. So this is gs, that is acceleration due to gravity at the surface, and this is acceleration due to gravity at a certain depth. Now again, the same thing, I'm going to take the ratios, that is gd divided by gs, so that we can get what is the difference. So again, if I do this, then I'll get the result as g rho. Instead of v, I'm going to write the expression for volume. That is, we all know that volume is equal to 4 by 3 pi r cube. So here, since it is at the surface, the radius will be r only for this particular sphere. So I can write it as g into rho into 4 by 3 pi r cube divided by r square. Now all of this is again being divided by g rho, again g rho and v. This particular v is the v at a particular depth. So the sphere has now actually become smaller. which means the radius is now r minus d. The radius of the smaller sphere is r minus d. So I can write this as 4 by 3 pi into r minus d whole cube divided by, again, it is not r square, it is r minus d whole square. R minus d whole square. So in the numerator, we can cancel this r square and r cube. Here also r square, r minus d whole square and r minus d whole cube. And between these two, I can cancel out g rho, not 0, but g and rho. 4 by 3 and 4 by 3. Pi and pi. So the only thing remaining is actually r and r minus d. So when we invert this, that is when we actually take it out, it will be r minus d by r. So if it is not clear, we are going to take gd by gs, which can be written down as g rho, g times rho times 4 by 3 pi r minus d, g r minus d by r minus d whole square, which will cut off with each other and r minus d will only be there, divided by g rho 4 by 3 pi r. So again, all of this and all of this will cancel each other out, and the only quantity remaining will be written down as gd by gs can be written down as r minus d by r. Right. Now again, the same thing I'm going to do. I'm going to just pull out the r's, cancel the r's out. So if I pull out the r, then this particular equation can be written down as gd by gs will be equal to r into 1 minus d divided by r. Right, if I take r outside of this particular equation, it is r by r into 1 minus d by r, because I have to take an r outside of the d also. So this will become 1 minus d by r. So I can just simply cancel out the r's, and the equation will read that gd, that is gravitational constant, acceleration due to gravity at a particular depth, is actually equal to gs, that is acceleration due to gravity at a certain on the surface, times 1 minus d by r. So again, what this equation also states is that with increase in depth, the acceleration due to gravity also decreases. The reason is because very simple, that is, if this is the earth, initially if we go in, it is true that the radius actually decreases, but we forgot to account to one fact, that is, the mass of the earth actually also decreases. The entire sphere becomes smaller. So that is the reason why even if we go at a particular height, because of the height factor, that is radius plus height, the acceleration due to gravity decreases. If we go inside the earth, the problem is that because the mass is so much smaller now, the radius is so much smaller now, even though the radius is smaller and acceleration due to gravity should increase, since the mass is now smaller, the acceleration due to gravity also decreases as we go inside the earth, and that is proven by this particular equation. So I hope you have understood everything about acceleration due to gravity, force, that is the universal law of gravitation, and finally what happens when we go up or inside the earth. So I'll meet you all in the next class with a new information that you don't know. Thank you.